On August 18, 2020, the destroyer USS Mustin sailed into the northern end of the Taiwan Strait. Every system on board, from the radar arrays on the bridge to the 96 missile launch cells on deck, depended on the same microelectronics the U.S. government was beginning to restrict. This restriction targeted the flow of semiconductors, the chips that run everything from smartphones to refrigerators. Today, the manufacturing of the world's most advanced processors is concentrated in a tiny number of facilities on the island of Taiwan. This creates a precarious economic choke point. A single missile strike on a Taiwanese factory would do more than destroy a building. It would instantly halt the production of new computing power, paralyzing global supply chains and causing hundreds of billions of dollars in damage. Computing power has become the new metric of national strength. In modern rivalry, the ability to process data has replaced the old reliance on brute industrial output. During World War II, victory was a matter of industrial attrition. Success was measured in tons of steel and aluminum, as American factories churned out more tanks, ships, and planes than all the Axis powers combined. Early electronic computers tried to bring logic to the battlefield, but they relied on vacuum tubes. These glass filaments were fragile and unreliable. They glowed like light bulbs, attracted insects, and frequently burned out, bringing entire machines to a halt. The breakthrough came with the invention of the transistor and the integrated circuit. By using semiconductor materials like silicon, scientists could fit multiple reliable electrical switches onto a single microscopic slab, doing away with the bulky, failing glass tubes. In the early 1960s, these chips were so expensive they were only used in the most demanding environments. The first big customers were NASA for the Apollo mission to the moon and the Air Force to guide its nuclear missiles. Inventing the chip provided the technology, but it didn't provide the scale. To define the coming era, the United States and its rivals would have to figure out how to mass produce them. The Soviet Union tried to catch up through a top-down strategy of espionage. After acquiring a Texas Instruments chip from the United States, Soviet ministers gave their engineers a simple instruction: copy it exactly, without any deviations. To support this, they built Zelenigrad, a secret city devoted to microelectronics. It was filled with elite physicists and researchers who spent their careers reverse engineering stolen Western hardware. This diagram shows why that strategy failed. Possessing a physical chip doesn't reveal the recipe used to bake it. You can see the circuit layout, but you can't see the specific temperatures, the chemical purities, or the precise timing required to fabricate working chips at high volumes. The microchip wasn't a secret that could be fully captured by spies. It was a product of practical trial-and-error manufacturing, a process the secretive Soviet system couldn't replicate. American firms realized that military contracts alone couldn't fund the necessary manufacturing advances. To drive costs down, they needed the massive sales volume found in the civilian market. Japanese innovators like Sony's Akio Morita pioneered this commercial scale. By putting transistors into everyday products like portable radios, some no larger than a matchbox, they proved that chips could be a mass-market commodity. This gave rise to Moore's Law, the prediction that computing power would double exponentially every few years as costs plummeted. To keep up, companies had to relentlessly overhaul their manufacturing techniques. They moved away from manual assembly toward photolithography, literally printing patterns with light. By shining ultraviolet rays through masks, they could etch microscopic circuits onto silicon wafers with more precision than any human hand. Even with automation, the final assembly and testing of these chips remained labor-intensive. As demand grew, American managers faced a labor bottleneck that threatened their profit margins. To keep costs falling, U.S. chipmakers began offshoring assembly to Asia. They built factories in Hong Kong, expanded into Singapore, and moved into Taiwan, utilizing a vast pool of labor to keep the Moore's Law engine running. The corporate drive for lower prices and higher volume had inadvertently created the world's first truly globalized technology supply chain. For the countries hosting these new factories, offshoring was about more than jobs. It was a survival strategy. Leaders like Taiwan's KT Lee worked to integrate their local economies with American tech interests. They wanted American corporations to be so reliant on Taiwanese assembly lines that the U.S. would have no choice but to remain invested in the region. This map illustrates the logic. Economic integration created a security guarantee. If American tech giants relied on Taiwanese factories, the U.S. military would be forced to protect the island to prevent a global economic collapse. This supply chain statecraft succeeded in turning corporate manufacturing into a geopolitical shield. Eventually, the feedback loop closed. The ultra-cheap, mass-produced chips originally designed for calculators and radios were so effective that the U.S. military began putting them back into the arsenal. Engineers at Texas Instruments attached a simple commercial laser guidance system to a standard bomb. A small silicone sensor tracked a laser reflection, allowing the bomb to adjust its own flight path and score direct hits. These weapons were deployed in Vietnam, successfully destroying targets that hundreds of unguided bombs had previously missed. It marked the end of the era of brute force attrition and the beginning of modern precision warfare. The global network of designers and factories built during the Silicon Age provided the West with a decisive lead in precision technology. But that same pursuit of efficiency has created a global bottleneck, centering the world's most critical technology on a few specific buildings sitting atop a geopolitical fault line.